Welcome to the fourth of 6 ACIS Web Services webinars. The Applied Climate Information System has been developed and is supported by the Regional Climate Center program. Today's webinar is on the station data call. It is at the heart of ACIS Web Services. The station data call returns daily or monthly climate data summary for a single station for a range of dates. It allows a range of summarization options that address the most common types of climate data requests that climate service providers are likely to encounter. Previous webinars on the station meta and general calls have addressed many of the details about ACIS Web Services. Thus, this webinar builds on these earlier webinars. The two remaining webinars on the multi-station data and grid data calls will build upon many of the concepts in station data. The station data call is the primary means by which ACIS transforms data into information. The call requires specification of a station, starting and ending date, and an element or climate variable. When only these parameters are specified, the call returns a listing of daily data values. A suite of optional parameters provide the real power of the ACIS station data call. Essentially, these specifications allow users to request numerous different temporal summaries of the data. For instance, by setting the interval and duration option to monthly and the reduction option to counts greater than 90, the station data call returns the number of days that exceeded 90 degrees during each month over the period specified by the starting and ending dates. The station data call also provides an option for directly returning station metadata, like those that can be obtained from the station meta call. Before we work with the station data call in the query builder, let's look at the call's required parameters in some detail. In terms of the required elements, any one of 10 station ID types can be used. Internal mapping of the station IDs directs ACIS to the proper data. For instance, data for Los Angeles International Airport can be obtained by specifying either this station's COOP, FAA, Wayband, WMO, ICAO, or GHCN ID, since this station is part of each of these networks. Currently, the use of the network code is optional, since the form of each of the different IDs is unique. Nonetheless, we saw that this value is returned as part of the ID in the meta field. For daily data, the starting and ending dates are specified as year, month, day. The use of dashes as separators is optional. When dashes are used, the leading zeros in the month and day can be omitted. Elements are typically specified by their abbreviation. The 5 common daily COOP observations are supported, as is the temperature at observation time variable. Common derived variables, such as heating, cooling, and growing degree days, and daily average temperature, are also available directly. The data can also be accessed by specifying the internal ACIS var major code number. If we return once again to the ACIS query builder and now choose station data, we see that the options included with the station data call are a bit more extensive than with the previous calls. In the simplest case, we can enter in a station ID, start date, and an end date. And let's say we're interested in maximum temperature, minimum temperature, precipitation. These are the only required parameters in station data. We hit submit, we see our conventional parameters and results objects. The parameters object that is sent to ACIS Web Services includes the 5 required fields: station ID, in this case the ICAO ID for LAX, a start date, an end date, and the elements we wish to have returned. The results object is a bit different than we've seen in the past in that it contains 2 name value pairs. First name meta, second name data. As in station meta, meta is associated with an object that gives information about the station's UID, coordinates, station IDs. Here we see that LAX is a member of a number of different networks, state, elevation, and name. The data field consists of an array of arrays. If we format our results, we see that each element of the data array consists of a date, the maximum temperature, the minimum temperature, and a precipitation amount. When only the required elements are specified in the StnData call, the call behaves very much like a lister, simply listing the relevant data values and dates corresponding request. Most requests will make use of the optional parameters. The first optional parameter is the interval. Interval describes the time step of the results object. The interval is daily when results are required for each day in the starting to ending date interval. If only a single value is desired for each month or year, then the interval is set accordingly. When an interval is specified, a duration is also necessary. There are only certain interval duration pairs that are meaningful. Notice that duration options include month-to-date, year-to-date, and season-to-date. Using year-to-date precipitation as an example, if we want a yearly total return for each day, the interval is set to daily. If we only want the total for the last day of each month, 12 values for each year, the interval is monthly. Duration can also be specified as an integer. Specifying 7 as the duration and daily as the interval allows 7-day precipitation totals to be returned. If duration is 7 and the interval is monthly, 7 monthly values are returned. Thus, the units day, month, or year of an integer duration always correspond to that set in the interval. Let's try a different example in which we specify some optional elements. Choose a co-op site this time, a starting date, and an end date. Look at snowfall data. I'd like to get that data on a daily interval, the daily duration. The daily interval duration combination essentially lists daily data. You can add a second element. In this case, let's say snow depth. Add that. Hit submit. Now see the parameters object. Still contains a station ID, starting and ending date. The elements field now consists of an array of objects. First case, we're looking for snow, an interval of daily, and duration of daily. And in the second case, we're looking at snow depth with the same interval and duration. Our results object, as before, contains two name value pairs, meta, along with our metadata object, and data, along with our desired variables. If we format our results, we can see that data is again an array of arrays, with an array specifying the date, snowfall, and snow depth for each date in our interval. Notice that the dates are inclusive in that we get data for both our starting and ending date. Values are returned in these arrays as strings. So on the 17th, we see that there is a trace of snowfall, a trace of snow depth, indicated by the T's. Let's try a slightly different request. Now we look at the same variables, but this time use the add option. We can add things such as data flags. Valid flags include trace, subsequent, accumulated, or missing, the time of observation, the station ID, the var minor, which specifies information about the data, and the network. In this case, let's add the time of observation to the snow depth variable. And for snowfall, let's request both the time of observation and the data quality flag. Submit. We can see that the parameters object looks very similar to the one we saw before, with one exception. The elms field now contains, in addition to name, interval, and duration, an additional name, add. For snow depth, we're adding the time of observation, and for snowfall, we're adding both the time of observation and the data quality flag. Our results object, again, contains two name value pairs, the first being meta, and as before, the second being data. If we format our results, you can see that the meta object contains the UID, the latitude and longitude, the station IDs for the station, the state, the station's elevation, and its name. This is the return we got for meta previously. The data element is a bit different. Data now consists of an array of arrays. Each array within the array is made up of 3 elements: the date as a string, and then 2 arrays, the first corresponding with snow depth, giving the snow depth value and its time of observation, and the second corresponding to snowfall, giving its daily value and its time of observation, along with its data flag. These observation times are given in local time. So at this station on January 1st, both snow depth and snowfall were recorded at 1800 local time. The data flags are generally blank, indicating that this station has good data coverage and quality. If the observation had failed quality control, the flag would have been set to missing. The only non-blank data quality flag is a trace that occurs on the 17th. Notice when we request the flag, the value on the 17th is returned as 0, whereas when we didn't request the flags, this value was returned as a trace. When the flags are requested, you can be assured that the data values that are returned are numeric. However, the flags must be checked to assure that these values are indeed 0, or the given value, and not associated with a trace, or perhaps an accumulated precipitation value. We can also see that this station experienced a change in its observation time. Prior to the 10th, both snow depth and snowfall were recorded at 1800 local. From the 11th through the 26th, the observation time changed to the morning. For the first part of this period, the obs were taken at 0800 local time, but later in the period, the obs were even earlier at 7 and 600. For our next example, let's start with a clean query builder. A common data request received by the RCCs is for a listing of daily data for a month, along with a summary of average monthly temperatures and perhaps total monthly precipitation. Often information about the warmest maximum temperature, coldest minimum temperature, and greatest daily precipitation amount is also desired. The summary option can be used to obtain these values with a single web services call. Let's try it. Use Wilmington as our station ID, and look at an interesting month when Hurricane Irene brought some precipitation. Look at maximum temperature, and looking at it daily and daily. And now if we look for a summary option, we have a number of summary code types. Max will give us the max value for the column. So in this case, if we choose max, we'll get the warmest maximum temperature between our starting and ending date. Min will give us the minimum value for the column. So again, in this case, it would give us our coolest maximum temperature if we selected that. Sum would sum the values, so it would sum the daily values, and this would be useful for, say, getting total monthly precipitation. Mean will average the values in the column, so this would be useful for getting, say, monthly average temperature. And we have a number of different count options. We'll discuss these later when we look at the reduction options. The newest version of the query builder also contains run as a summary type. This will be discussed at the Web Developers Workshop and in the ACIS Web Services documentation. So for this case, let's do a max. It'll give us the warmest maximum temperature during that month. We'll add that as an option. We'll also request the minimum temperatures. We'll summarize them as a min element, and we'll also look at precipitation. But in this case, the summary options will be interested in the sum, so we'll look at the total monthly precipitation, but also the max, the greatest one-day max precipitation. Hit submit. We'll format our results right away. If we look at the parameters object, really all we've done is built upon what we have before. We see in our Elms field, I'll again have an array of objects. Our first object is maximum temperature, again with an interval of daily and a duration of daily. But now we've added that we'd like to summarize those daily values and return the max. We have an object that corresponds with the minimum temperature, again daily, daily. In summary, we'd like the, in this case, monthly minimum temperature. And then in the last object, we have our precipitation object, where we're requesting precipitation, daily, daily for interval and duration. And for our summary, we'd like two things. We'd like the monthly sum, so that would be our total monthly precipitation, and max, that would be the greatest precipitation on any one day. We look at the formatted results object. We see our return. Again, the daily daily is going to be our listing of data as an array of arrays. In each, we get the date, the maximum temperature, the minimum temperature, and the precipitation for that day, going down through the month. And then we have an additional name value pair. In this case, our name is summary. And we've asked for basically three summaries. For the max column, we've asked for the maximum of the maximums, and we can see that that is a 97. So in other words, if we went down this column of max temperatures for each day in the month, we see the highest temperature recorded was the 97. For the minimums, we asked for the coldest minimum temperature, the lowest minimum temperature, and we see from this column that a 56 is the low for that month. And then for the precipitation column, we've asked for two things. We've said sum all these precipitation values, and we see that the total monthly precipitation at Wilmington during August of 2011 was 14.7 inches. And we've also asked for the maximum precipitation. The one-day maximum precipitation was the 5.38 inches that fell on the 27th. When we specified a summary, an additional box labeled add appeared. Add has three options: mcount, date, and rmcount. Rmcount is used with the run option, as is the box for summary number that now appears in the query builder. We selected date in our example for maximum daily precipitation. Let's just look at the max. Have that as our element. Hit submit. See in the parameters objects, our summary object contains both a reduce field and an add field. In this case, add is date. And our formatted results, again, show the summary field, but in this case, we've asked for the max, which is the 5.38, but it also now shows the date on which the 5.38 occurred. Since summary will return a value regardless of how many missing values are in the requested period, the add option mcount is useful for quickly seeing the number of data values upon which the summary is based. All of our previous examples have used an interval and duration of daily. Suppose we choose something other than daily. In this case, we'll choose an interval of monthly and a duration of monthly. When specifying most interval duration combinations, a reduction is required. The reduction code tells ACIS how to temporally summarize the data. For instance, in our example with an interval of monthly and a duration of monthly, the reduction code specifies the desired analysis. If we chose the reduction code max in combination with our element of snowfall, our return would be the highest daily snowfall value in each month between our starting and ending dates. Total monthly snowfall could be obtained by using sum as the reduction. The number of days with an inch or more of snowfall would use count as a reduction type. With count, we must also specify an operator, either greater than or equal to, greater than, less than or equal to, less than, equal or not equal to, and a threshold. Percent gives the percentage of daily values that exceed the threshold. Fraction gives us percentage as a float value. The newest version of the ACIS query builder contains three additional reduction types. First and last give the first or last occurrence of a daily value exceeding a threshold. These reduction types might be useful for determining the date of the last spring freeze. The run option is similar to that discussed in summary. It shows the occurrence of consecutive daily values exceeding a threshold. This might be used to analyze heat wave frequency. In our example, let's use the reduction of count, greater than or equal to an inch. The reduction also contains an add option. As before in summary, the add option can either be mcount or date. Let's use mCount. This will show us the number of missing values in each month. And let's add an additional element. In this case, we're going to specify max missing. What this says is only do the reduction for those months that have this number or fewer missing observations. In practice, these two elements most likely would not be requested together. However, here this provides a useful way of demonstrating how max missing works. Parameters object contains the conventional station ID, starting and ending date, and our elements array. The elements array contains two objects. First object is snow, monthly, monthly. We've asked for a reduction. The reduce field is an object. It tells us two things in this case. It tells us what reduction we want. So reduce is greater than or equal to 1. And it also includes an add field since we requested that the monthly missing count be added. The second elements object is the same, except an additional name field appears. In this case, it's the max missing field with 3 specified. At our results object, we have the meta field as always, and now a data field. Data field is an array of arrays. If we format it to make it more clear, each month is an array. The array contains the month, so here July of 1993, and then 2 additional arrays. The first one is the number of days with snowfall greater than an inch, so of course none in July, and the number of missing values in that month, there are none. If we look further down, a good example here is in January of 1994. See our date. Our first array says there were 9 days with greater than an inch of snow at this station. However, 19 days were missing during this month. So then when we look at the second element we requested, the monthly counts of snowfall greater than or equal to an inch is missing because 19 exceeds our max missing value of 3. If we look at December of 1994, we can see there are 3 days with greater than or equal to an inch. Only 1 day is missing during that month. So in the second element, the count is not missing since 1 is less than our max missing value of 3. Let's look at one final example in this already long webinar that uses the normal option. Look at the parameters object. See that I've picked my favorite station, Ithaca, and I have 2 elements. I have maximum temperature with an interval of yearly and a duration of yearly. I've also included a reduction of mean, so this will give me annual average maximum temperature. In the second elements object, I've also included maximum temperature with the duration and interval of yearly, but I've also added the normals option, normal of 1. So what will happen in this option is I will get the annual maximum temperature normal. We go down to the results object. See, we have our meta and data fields. Data is an array of arrays like it's been in the past. If we format the results object, we see that each array in the data array consists of 3 values. The date, in this case it's just a year since our interval is yearly. The annual average maximum temperature for each of these years. And then in the third column, the normal annual average maximum temperature. Clearly each of these values is the same since the normal is consistent through the period. There are a number of other reductions and option parameters that we can set. However, instead of going through each of these individually, probably be a good exercise for users to try the query builder on their own and look at the types of analyses and products that can be generated. Hopefully looking at some of these will give you some ideas for climate services products that can be developed using ACIS web services. Viewers who plan on attending the ACIS development workshop in August might use some of these ideas for the product they develop at the workshop. The workshop will feature hands-on ACIS development guided by Regional Climate Center staff. Web tutorials such as this will provide the necessary prerequisites for the workshop. 2 additional webinars will be released in the coming weeks. Since space is limited at the workshop, we ask that interested participants please register at the following website.